Hi, hello everyone. In last class we have seen what a relation is and when it can be reflexive, symmetric, antisymmetric and transitive, and what is inverse of a relation, what is the complementary of a relation, all these things, and what are the operators that can act on the relations. We have seen couple of operators, select operator and projection operator, and we have seen their applications in relational database management systems. In today's class we will see how relations can be represented smartly, and we will see when do you call a relation an equivalence relation. This equivalence relation has got lot of applications. If you go to software testing and all, we would like to equipartition the data, test data, so that we can take one sample data from each partition and test that particular thing and be sure that the whole partition data will be as if the whole partition is tested. This equipartitioning of the test data we can do, and then we will see what a partial order is, and it has got lot of applications. It basically orders the base set with reference to the relation that we are speaking, and then we will see what a lattice is. To start with, we can represent a relation just by representing it as a list or table. If I have to represent, if I have got 3 boys and 3 girls, say something like this: Susan, Mary, Sally are girls, Joe, Fred, Mark are boys, and I am talking a relation on these guys, and the relation I am talking is boys versus girls. This is the Cartesian product I have got, and I have got 3 boys and 3 girls, and here I am talking likes relation. The moment I say this is at like, this is a relation, I will have likes is subset of B cross G, and this relation is going to have the 3 tuples. I am going to define it because the relation is what I am defining it here. Joe likes Susan, Mary Susan, and Joe likes Mary, and Fred likes Mary, and Mary likes Sally. This is the relation that I am talking here. So my likes relation is having 4 tuples. What are the tuples that it will be having? Joe comma Susan, Joe comma Mary, Fred comma Mary, and Mark comma Sally. These 4 tuples that it is going to have. I just say this, I just likes is equal to these 4 tuples I write. This is one way of representing a relation. Another way is I actually go to B cross G. That means that I will take each tuple from B cross G and I associate true when a particular boy likes the girl, otherwise I call it false. This is the function that I am defining. Basically what I am saying is I can define a function from B cross G to true comma false, and f of Joe comma Susan I give the value true, and Joe comma Mary I give value true. F of Fred comma Mary I give value true. F of Mark comma Sally I will give its value as true. For all other tuples in B cross G I am going to give the value of false. So the relation is equivalently represented by this particular function, isn't it? These two are laborious if you see it. In fact, the other way of looking at it is a relation can be represented by means of a nice function. Here, let us see, can we have other way, smart way of representing these things? There are two ways of representing a relation. One is using a matrix, another is using directed graph. The directed graph probably we may see when we do graph theory, but right now let us see how a relation can be represented by a 0 1 matrix. Here I put my rows as Joe, Fred, Mark, I columns as Susan, Mary, Sally. So these are the boys and these are the girls. Then for Joe and Susan, I'll put 1 if Joe likes Susan, otherwise I am going to put 0, because my relation is defined in such a way that Joe likes Susan, I am going to put 1 here, and Joe likes Mary, so I am going to put 1 here. Joe does not like Sally, so I am going to put 0 here. Similarly, Fred does not like Susan by the definition of the relation that we were given, hence I put 0. This is how I am going to define the relation. So a relation can be very much represented by a 0 1 matrix as well, and we will see the advantages of this. Say we have got relation A on the set A, that means relation is acting on A cross A, and say this particular relation is being represented in 0 1 matrix, just the way that we have done in the previous example. Imagine you have got any generic relation R which is working on the set A, and think of imagine its 0 1 matrix representation. Then I can always say that if that particular representation is having all diagonal elements as ones, what can I conclude? Basically my relation is acting on A. Suppose if A is having the elements like A1, A2, so on, A10, what I am going to have here, or I am going to have 10 rows like this. I am going to have 10 columns like this, isn't it? Then when there is when A1 comma A2, this particular tuple, if it is there in relation R, I will put 1 here, otherwise I don't put anything. That is how my matrix will be looking like. Suppose the matrix that I have got, the matrix that I am having has got all ones in the diagonal. That means that A1 and A1 are related, A2 and A2 are related, A3 and A3 are related, A10 and A10 are related by related. That is what it means. I have put 1 means A1 and A1 are related. I have put here 1 is A2 and A2 are related. I have put 1 here is A10 and A10 are related. For all the elements of A comma A is related to A. It means that the relation is reflexive. Hence, this particular relation, the relation corresponding to this matrix is reflexive. I will be able to say if all the diagonal elements are 0 or 1. So, to wrap it up, if I have got a relation R that is working on a relation on the set A, then if somebody comes and gives me the 0 1 representation of that particular relation, then I look at the diagonal elements of this particular matrix, and if all the elements of the diagonal are 1, then I can definitely say the relation is reflexive without actually looking into the relation. By this particular representation I will be able to say this is reflexive. And if all the diagonal elements are 0, then I say that it is irreflexive, because A comma A is always belonging to the complement of the relation R. That is why none of the diagonal element is having 1 as its value. All A comma A for all A in A is belonging to the complement of this particular relation that is given to us. That is why all the diagonal elements are assuming the value 0. Hence I say this relation that we were given, which has been represented in the form of 0 1 matrix, is irreflexive. And if the matrix that is given to us is, whenever Aij is 1, then if you are able to say Aji is also 1 in this particular matrix, if Aij Aij is 1 and then Aij is 1 and Aj is also 1, and this is holding good for all I comma j, then I can say that whenever Ai and Aj are related, Aj and Ai are also related. That means it. Aij is equal to 1 means here Aij is equal to 1 means Ai, the element Ai and element Aj are related. And whenever this is 1, say from this matrix I am able to see that Aj is also 1. That means Aj and Ai are also related. Whenever it is happening for all I comma j, for all the elements of the set A, then I can say that this is symmetric matrix. When the matrix that is given to us, which is actually representing a relation, is having this particular property, the property of whenever Aij is equal to 1, then Aj is also equal to 1. This particular property, when it is holding good for all I comma j, then I can say that this particular relation is symmetric. And when we have got Aij in this particular matrix, say this is the matrix, I say Aij is equal to 1, that means ith row and say jth column. Suppose this is the guy, this is ith row, say this is ith row, and say this is the jth column. When I have got ith row and jth column is taking the value 1, and then in the matrix I found out Aji, that means jth row and ith column is taking the value 0, and this is true for all I comma j, then I say that the relation is antisymmetric. If Aij is 1 and Aji means ith row and jth column is 1 and jth row ith column is 0, and this is happening for all Ij, then I say the relation is antisymmetric. Actually I don't know what the relation is, how it is being actually defined I don't know, But if you give me the representation, matrix representation of that relation, I'll be able to say, by looking at the elements of this particular matrix closely, I'll be able to say that the relation is reflexive, or it is irreflexive, or it is symmetric, or it is anti-symmetric. So we have got a relation R that is working on the set A. That means R is basically subset of A cross A, and R might be defined with some predicate, with some logic R has been defined. Then for all we know, R can be reflexive or it need not be reflexive. If it is reflexive, it is fine. If it is not reflexive, what should we do to make it reflexive, to get a reflexive to make it a reflexive relation? We simply we'll take each element of A and see whether A comma A belongs to R. If it is belonging to R, we don't have to do anything. Suppose A comma A does not belong to R for a given R, then I will add A comma A to R. I will add some elements to the relation that is given to me. What elements I am going to add is A comma A, the tuple A comma A. I am going to add it to relation R to make it reflexive. Okay. So whatever the tuples that are missing in the set in the relation R, for not having this reflexive property, those tuples I am going to add to R for it to make for it to become a reflexive. By adding some elements like A comma A to R, I am making relation R reflexive. Basically, that particular relation that we get out of this operation is called closure. The reflexive closure of a relation R on A is obtained by adding A comma A to R for each A in A. You just add A comma A for all A. Of course, for some A1 comma A1, it is already there, you don't have to add it. Whatever is missing, you just add it to get a reflexive closure. Similarly, what is symmetric? Given a relation R, it need not be symmetric, isn't it? What I mean here is A comma B is in R. It doesn't mean that B comma A is also there in R. It may be there, it might not be there. If it is there for all A comma B, then you say that is symmetric. Suppose it is not symmetric, then what you do is you just, for each A comma B, you just add B comma A to the relation R. You add some more tuples to R to close it with respect to the symmetricity. So R is given to us, you add some more elements to get a symmetric relation. What elements you add is, for each A comma B, B comma A, you add it to it. If it is already symmetric, you don't have to add any element to your relation R. If it is not, you just add few more elements so that the relation becomes symmetric, and this particular new relation is called closure of relation with respect to symmetricity. Similarly, transitive, we say a relation is transitive if A comma B and B comma C belongs to R, then A comma C is also there in R. We say the relation is transitive. But given a relation, we don't know whether it is transitive or not. What does it mean? Given a relation, you can have tuples like A comma B and B comma C in R but A comma C is not there in R. Such a relation cannot afford to be a transitive, cannot afford to be a transitive relation. You keep adding A comma C whenever A comma B and B comma C are there in R. You keep adding these tuples. By adding these tuples, the resultant relation is called a transitive closure. You are closing that relation by adding some more elements with respect to the transitive property. It is being closed. That is what it means by closure of relations. Okay. You got a set and say you got a relation that is working on the set, that means R is a subset of A cross A, and say this R is reflexive, R is symmetric and R is transitive. Suppose it is having all these three properties, then I say R is equivalence relation. So this equivalence relation gives lot of flexibility in partitioning the basic set A. Let us see how it is. We will take an example and see how does equivalence relation looks like. Suppose H is the set of all human beings. I am defining my relation as this way: x comma y belongs to H cross H such that x has same mother as y. This is the relation that I am defining. Now let us examine whether this relation is an equivalence relation or not. First of all, is it a relation on H? Definitely yes, because it is taking tuples from H cross H only, and afterwards it is applying some property. Hence it is a relation. Is it reflexive or not? For it to be reflexive, you have to take an element in H and you have to prove that A comma A belongs to R, isn't it? So take an element A and then I make this statement: A has same mother as A. Is it a true statement or false statement? It's very much true statement. A and A are having the same mother. Hence the relation R here is a reflexive relation. Okay, and now I say this: A comma B belongs to say R. Then what does it mean? It means I'm proving actually symmetricity here, symmetric property here. I'm saying that A comma B is in R, relation R. What does it mean is A has same mother as B. Once I have got this statement, I can also say that B has same mother as A, isn't it? I can say this statement as well. When I make this statement and this statement is true, what does it mean? B has same mother as A. That means that B comma A is going to be in the relation R, because that is how you have defined the relation actually. All the tuples for whom mother is the same, so B comma B has same mother as A is also true because of A comma B belongs to R. I can say that B comma A is in R. So for any A comma B that is there in the relation, I am able to show B comma A is also there in the same relation. Hence my relation is a symmetric relation. Let us see how it is transitive. suppose A comma B is in the relation R and B comma C is in the relation R, then we have to show A comma C is also there in the relation R. What does it mean? Then we can easily say that this relation is transitive. When I say that A comma B is in R, it means that A has same mother as B. And when I say B comma C is in R, it means B has same mother as C. Because of these two statements, I can obviously infer that A has same mother as C. This is but obvious. Hence, I can say, because A has same mother as C, I can say that A comma C is also there in this relation. Hence, this relation that I am talking here is a transitive relation. Now what we have got? We have got a relation R that is defined by the predicate X has same mother as Y on the set H, that is set of all human beings. Is this particular relation is reflexive, symmetric, transitive. Hence, this relation is equivalence relation. We will see the significance of this particular equivalence relation. Now let us see some more examples before getting to it. Suppose my base set A happens to be set of all strings. Set of all strings, string I mean by a simple English word which is a string of characters, isn't it? On this particular set of all characters, I am defining a relation R such that two strings A and B are related if and only if they have the same length. This is how I am defining the relation. When I define my relation like this, R is defined as A comma B, where A and B are two strings such that A and B has same length. This is the relation that I am defining. Now, in the same way that as we have done for the previous example, this relation is very much a transitive, a reflexive relation, because if X is a string, X and X has got the same length. If X and Y are the strings of same length, then Y and X is also of X and Y also has the same length, string length. Hence, we say this particular relation is symmetric. And whenever you say X comma Y in R, that means X and Y has the same length, and Y comma Z in R, that means Y and Z has got the same length. When these two things are given to us, we can obviously say X and Z are also having the same length. Hence, we can say that these two imply us that X comma Z belongs to R, because X and Z are going to have the same length. Because this particular relation defined like this is satisfying all these three properties, it is called an equivalence relation. Now you can just do the same thing for all the below. Integers A and B have the same absolute value. This relation that is acting on the set of integers is also equivalence relation, and real numbers have the same fractional part acting on this relation acting on the set of real numbers is also equivalence relation, and A and B have the same residue modulo m, means you have got set of integers. Here I am defining a relation called m on set of integers, like this. The relation is being defined like this: A comma B is going to be there in this relation provided A, the residue of A when it is being modulated by M should be same as B mod M. When this particular property is being satisfied, then A comma B is going to be there in the relation, otherwise not. This is also an equivalence relation. Now what I am going to define is an equivalent class. Suppose I have got a set A and I have got a relation that is working on the set, and say this R is equivalence relation. Is an equivalence relation, then I can define equivalence class. I take an element A in A. The equivalence class of A is defined like this: set of all B in A, set of all elements in B, such that A and B are paired up, or A and B are there in this particular relation. So given an element A, it might be paired up with a number of guys when the corresponding tuple is there in the relation R. When the corresponding tuple is there in the relation R, I will consider all such elements in A with which A is being paired up in the relation R. This particular set is called an equivalence class. You are getting what I am saying? Given an element A, I look at all other elements of the set A with which this element A has been paired up and the tuple is there in the relation R. I consider all such elements. All such elements constitute the equivalence class of A. We will do it with an example. When I have got strings A and B have the same length, when this is the relation that I am talking on the set, say the set of all strings, this is the relation that I am talking, and I will take a string. I will say suppose I am talking of this in English, English strings, English words for that matter. What is the equivalence class of cat? When cat, I consider it as a string. What is the equivalence class of cat? All the English words that have got the string length as 3 are going to be there in this set, in this class. Mat, ant, all the possible English words who has got 3 characters in it are going to be there in this set. Why they are going to be there in the set, in the equivalence class of cat? Because any element you take in this set, say mat and cat has got the same string length. all the elements which are having their character length as 3 or string length as 3 are going to be there in the equivalence class of cat. So given a word, I will be able to talk about its equivalence class. All the words which are having the same length as A, that is what the equivalence class. When we say another relation, we will see integers A and B have the same absolute value. This is the relation. This we can easily see that this relation is an equivalence relation. Now I am asking you, what is the equivalence class of say 2? What is the equivalence class of 2 with respect to this relation? I will say it is minus 2 comma 2, because 2 and minus 2 have got the same absolute truth. 2 comma minus 2 is going to be there in the relation that I am talking of. The relation that has been given to us, 2 comma minus 2 is going to be there in that relation, and 2 comma 2 is also going to be there in my relation, because 2 comma 2 is having the same absolute value, and no other values can be here, because you take any other integer other than 2 and minus 2, it is having a different absolute value than 2. So the equivalence class of 2 will have only 2 elements, that is minus 2 and 2. So if you carefully observe now, what is actually an equivalence relation is doing on the set A, it is basically dividing the base set A into some partitions, isn't it? You take any element of the base set A of say R is a equivalence relation, you take any element in the base set A, then you can talk its equivalence class. It may be having more than one element, we do not know how many elements it will have. How many elements that it will have depends basically on how the relation has been defined. For example, in this case, this particular relation, this particular equivalence class has got 2 elements. Basically, this equivalence relation is partitioning the set A into some parts. What I mean here is, given an equivalence relation, we are able to construct some classes. How do we construct? You take an element of A, element of A, and then it will give you a partition. So finally the set A has been partitioned into these equivalence classes, and the beauty of this is, you go to an equivalence class and you pick up any 2 elements in that class, both of them will be equivalent to each other with respect to the relation that we are speaking of. When I say minus 2, when I say what is the equivalence class of 2, it will be having 2 comma minus 2. What I mean here is, these 2 elements are actually equivalent with respect to the relation that we are speaking here, the relation of having the same absolute value. These 2 values are actually the equivalent. So you have got a set, and the equivalence relation is able to partition your set like this. That means that all the elements in this partition, you take any 2 elements in this partition, they are those 2 elements are equivalent with respect to the relation that you are speaking. Whatever the relation that you are speaking, they are equivalent with respect to it. And if you take an element here and an element in another partition, definitely they are not equivalent, they will be different. But within a partition, all the elements are equivalent to each other with respect to the property that you are speaking of. We will do with an example and see it. Suppose we have got the set of all human beings in the universe, and then I am talking a relation here. I am talking the relation here like x comma y are there in the will be there in the relation if x and y have got the same date of birth, Is this an equivalence relation? Definitely yes, because it is reflexive, symmetric and transitive. And what is going to happen here is, you take any date, for example the date of say 26 June 1981, say if this is the birthday of say Ramesh. The equivalence class of Ramesh tells us what? All the guys, all the human beings who have born on this date are going to be there in this equivalence class, isn't it? So all the guys who are there in this particular equivalence class are having the same date of birth. You take any two guys, they are actually equivalent with respect to this particular property. So if you roughly take, there are 100 years, maximum human age is taken as 100, and 365 days on an average if you take, more or less you will have 100 into 365 partitions. Whole human beings can be partitioned into 100 into 365 sections, and each section is having, all the guys in each section are having the same property, equivalent property, that is all of them have got the same date of birth. So basically an equivalence relation partitions the set A into some sections, and each section, elements of each section are equivalent.